Thanks, Marcus. Let me start by showing a few of the examples that you asked us to show. First thing on the cell selection, someone was asking how we can count how many cells and how many burst cells are in this image. As I think I showed already in the other two occurrences of this and today's tutorial, either one can do a component measurements of the segmentation that was extracted from the image above and do basically ask for a property called label count, or as I was putting this into a data set object to nicely visualize what are the different properties for different shapes, a simple length of a data set can be used also to extract how many cells were segmented out of the image. Also, after the selection was done, this can either be done on the dataset level or with select components, which takes the segmentation in rather than taking the dataset in. Again, one can do length of a selection or do a label count on cleaned up segmentation, basically. So this was one question that I wanted to quickly mention. The other thing was that was asked earlier in the talk was on that fish tank data set. How can we easily track the result of the segments? And yeah, of course, I lost the computation. I didn't want to wait on the computation anymore, so I processed it in the background before. Now we'll have to wait probably a little bit. But here you can see that I have two dots on the two fish showing where they are, and if I hit play or basically drag this player icon, you would see still the marks on the images. Of course, I would see some of the reflections as well here and there. But also another thing that I did, let me see if my segmentation can finish in time and quickly. This shouldn't take a whole lot of time for me to have the position of these centroids extracted. And another thing that I did further below is that I was just showing and tracking centroids of these of the detected and segmented fish. And now you can see if I do this in steps, these two dots that are small now on the screen are the initial location detected for the fish. And this is the second location detected for them, and we can go forward with where they move and basically track it. If I continue, this gets messy, but or I don't go beyond 20 anyways, but the heat map that I showed before is basically a clear indication of where the fish were detected. Another example on morphing that was asked, this was in fact Markus's notebook from one of the previous year's workshops, but I didn't know if he can find it quickly on his machine, so I'm showing it. As I said, tinplate spline is a very common interpolation to want to do. And since this is not built into Mathematica, but it doesn't take a whole lot of Mathematica code in order to implement such a transformation. And here we have some markers on the two images of that you can see of Marilyn Monroe and Arnold Schwarzenegger with landmarks on their eyes, nose, mouth, and chin. And then a transformation that takes one image to the other, that morphs one image to the other, and you can see a middle state in this image, or even with a manipulate, you can see how we would go from basically one image to another. These were the three notebooks that I could prepare in the meantime to show. I don't know if Markus had seen other questions that want to answer or demonstrate.
I will try to come up with an answer in the short time that I had to prepare now. There's a question regarding the temperature resolution and I think the mapping between color and temperature. So I assume that's a physicist who asks that. We do have color. Let's see. I'm not sure if I can find it so quickly. We have color data, and there is color data on that mapping somewhere. I quickly have to look for it. Here, oh, there we go. So we have color data on temperature, and this will allow us to basically convert a black body radiator at a certain temperature to convert that into the prominent color at which that particular radiator would glow. And you can use that here with colored data. Now the question though is here physical, what kind of physical colors we have. Let me see. I can type this in. So we have a black body spectrum, we have hypsometric tones, and then visible spectrum to display. So how do I do that? Do I have an example here? Schemes and collections. Sorry, this is not well prepared, but then I don't have time to prepare this. Let's try to just do it like this. This is a physical spectrum. Let's do the... I'm not sure if I have to combine these two or if I can use that separately.
Just the black body spectrum will give you that, Markus.
Okay. All right, so that's black body spectrum, and the nice thing is that you can also specify here the wavelength of that particular, the degrees in Fahrenheit or not Fahrenheit, in Kelvin or Celsius, I assume. That will then give you the corresponding color, I guess. Yeah. So if you have something 1,000 degrees hot, you will get this particular color. If you get something that is much hotter, like 4,000 degrees, it's already yellowish, and if you're up to 10,000 degrees, it already will look like a blue body. It's so hot. So that was the quick answer about the relation between color and temperature. If you have anything in the meantime, Shadi, be my guest. Otherwise, I have to search for new questions that I can answer.
There were questions, just a general response. There were questions about astronomical applications or geographical applications and so forth. I would like to mention that Mathematica in general is very general purpose. There are, of course, some functions that are very much specialized and targeted to any of these fields. But in general, since we are not really application-oriented and application-specific, all the tools are designed towards being applicable to different fields. So even if you don't find something that is immediately available and is really targeted to your application, there is typically a good way of combining one or two functions and get where you want to get. And also, we are all looking for feedback anyway. So if there is anything that is missing and important for your workflow, let us know. And we would love to hear any feedback about our work in general anyway. So anyways, this was a general comment about a couple of questions I saw.
There's a question about from Simon about the heartbeat application, and it says, did you average over adjacent pixels to detect a color variation? And the answer is yes. If you go again, have a look at this color case. Basically, the color change that you have, well, every color pixel has a quantization, at least in a byte image, of between 0 and 255. Or if you go in the interval from 0 to 1, the quantum step from one color to the next is 1 over 255. So that's the smallest color change that you can have in a byte image. And the color changes that are due to the heartbeat on the skin are about 1/4 of that. So you would have to have roughly 1,000 different color shades at hand in order to show that particular color change in a single pixel. However, due to statistics, by just taking a large area of pixels, and just by taking 100 times 100 pixels here, I have 10,000 pixels, I can do good statistics. I can now also find slight changes, statistical changes that are much smaller than that quantum color step. And that's how this works, basically. Take average over a lot of pixels, and then you can also actually detect very minor color changes. The only trick here, though, and that's why the whole pre-processing was necessary, is you have to make sure that you don't have any other motions or artifacts that will lead to signals. So any kind of motion may then also change the average color because darker areas move in or lighter areas move out. So that's the trick in getting these subtle color signals into Mathematica. Shadi?
Question about cloud, Wolfram Programming Cloud. I just checked, we are at version 10.1, which is the latest released version of Mathematica, which should cover most of the things we showed in our presentations today, maybe except a couple of very new features that are not yet available. Typically, Wolfram Programming Cloud is in sync with the version that was released for Mathematica. It might be behind just by a couple of weeks or a month or so, but it shouldn't be behind by much bigger than that.
Okay, here is a question about, is there a way to transform the graph of a function into a 3D volume which could be the result of revolving the graph around the x-axis? Let's see, I think I can answer that particular question live. Let me see. And the command is revolution plot 3D. So how does it work? Let's go to the reference page. Revolution plot 3D basically takes a function f, typically in the z direction, but I think you forgive me for using z instead of x, and then basically using that functionality and revolving around it, and then creating maybe a shape like here, a torus. So if I would take this particular example, then this would, well, actually, this is parametric plot.
Sorry,
even.
Markus, I don't think we can see your screen, Markus. Did you stop sharing?
No, not intentionally.
Oh,
okay.
Okay, we can see now.
Right. So I have here, the key to the question is there is a command called revolution plot, which allows me to either have a parametric function or just a function to define a revolving body like this here. And then what I could do, I'm not sure if that's possible yet, convert that into a solid and into a volume, but that I would have to try to see if that's already working. Is it possible to rasterize just like this yet, or did we not? Well, no, that's just
doing I know of. This rasterizes. Yeah, this converts that to a 2D image. A lot more of these types of conversions are in the pipeline, though. So between images and graphics 3D.
Yeah, but Shadi, we had a hack for that. I just can't think of it. But just maybe then to outline how the solution would work is you do basically this plot, then you do a rasterize the 3D volume, so they just at least get the surface of this revolution thing. You get an empty body, so to say. Then you can apply the filling transform to fill up that shape, and that should give you then an image 3D volume that you have been requesting. But this rasterize step, that is something that we do have somewhere, but it's a hack that I don't know by heart now. Sorry for that. Shadi?
Sorry, I don't know which function you're referring to either.
Yeah. Well, one way to do it is to only do it layer by layer and rasterize each layer. That's one way to do it, but there were better ways to do it. Well, this will take too long. I don't think I can answer this readily.
Okay. Questions about import and export. There are a bunch of file formats already available, and of course you can go to the explicit functions import and export or individual file formats, right, like JPEG, TIFF, PNG, and so forth. Unfortunately, I saw a couple of questions on microscopy file formats, the ones common in microscopy. We don't have most of them available right now, but again, it is in the pipeline and hopefully it will be available soon. As far as export is concerned, everything that can be generated in Mathematica, both 2D and 3D images, can be exported to all the available image file formats that are supported, basically.
The question is, for analyzing video frames, videos frame by frame, is out-of-core processing recommended? Yes. I mean, as long as the data fits into memory, you shouldn't bother really. Memory is cheap, and if you have 4 gigabytes of memory and your animation only takes up 1 gigabyte, you don't have to do out-of-core processing. But if the data becomes too big or so, then out-of-core processing is recommendable. And we do have out-of-core commands that are called, what is it called? Shadi file.
Image file apply, image file filter, and so forth.
Right. So basically, just for those who don't know what out-of-core processing means, could I have the screen, please? Okay, there you go. Okay, we have commands in Mathematica, typically starting with image file, and they allow you to process image data, large image data, in such a way that you do not have to load the entire image or movie or gigantic lens map into Mathematica, but it can work on parts. And one of these key commands is image file apply, where a function is acting on data coming from an input file, and the resulting image is then put into an output file. And this is an example here. You get data from test image apples. You basically do a color invert, and then the result goes into a file path, and that's where then the result is stored. And even though for this particular image it's not necessary, it's not big enough, it would still work. And we have other commands like image file filter to apply filters piece by piece on large images onto large images. And the third command for out-of-core processing would be image file scan, which allows you to specify a function that then would be applied to one patch at a time.
Also look out for all the other events that are coming and courses that we are preparing towards image processing or other topics of interest to you. We would be happy to host any specific events or talks if your group is interested in that, and basically have a dedicated talk for your team, which is also in a smaller group targeted to your needs, and basically in touch with the rest of the teams that you're working with. That's also another possibility. You can email those to training@wolfram.com, or again, Cliff might be the right person to go to if that's something needed. I would like to also emphasize on the fact that 2 hours was very short to show more things. I see a question on what would be the rule of thumb to select the right segmentation technique out of the many that are available in Mathematica, or in general in the literature. There are so many algorithms suggested for segmenting objects or regions out of images. And this virtual conference was basically the beginning of us moving towards having material to show people and give these hints and rules of thumb to people to learn how to use image processing routines to their problems. I can speak to this particular problem as well, but also keep an eye on upcoming events for image processing and other ones, because we do think that this is an important step forward to give you hints and tutorials on how to go about your problems. As it is specific to segmentation, however, Markus tried to show it a little bit, but again, the time was very much limited. Typically, if your foreground or segment of interest is very much in contrast with the background, Simpler algorithms like intensity thresholding or hysteresis thresholding, being binarized and morphological binarized, would do the good job. Markus showed simple thresholdings like binarize and local adaptive binarize or morphological binarize, which are typically basically looking at the contrasting areas between foreground and background. But as we go one step further, and then all of those are doing binarization. So basically they're looking at two segments, one foreground, one background. Clustering algorithms are multi-region segmentations. These are trying to figure out how to separate different colors or different ranges of intensity values if you're looking at a grayscale image, and try to come up with components and clusters that have similar ranges of intensities, basically having multiple cutoffs in the histogram of the pixel distributions. Next come region growing. These will be useful when, for instance, in this case, you have one region that is slightly different in color and intensity from its surroundings, being the tumor, or in this case, I think being the eye or something like that. And then you try to grow from that one seed or multiple seeds that you have selected, and you know your object of interest is not connected to the rest of the image, even via one single pixel, because if it is, then the growing algorithm will basically leak into some other regions and you don't get the proper segmentation that you're asking for. Watershed is a slightly more stable one, and it's typically it's typically combined with techniques like Gaussian filter for smoothing and then gradient filter to find the edges of the regions and so forth, in order to find a better segmentation between one region and the other, as Markus showed this before, and as well as that maze example. Chanveza binarize and also the Groscut binarize are the ones that are aware of foreground and background at the same time, and they try to grow both foreground and background. In this case, we are saying that our foreground is red, background is blue. Try to find red and blue regions and grow both of them until they meet, they reach each other, and then that would be a segmentation. Or in the case of Groscut binarize, as Markus showed, we have markers for foreground and background that are sometimes can be very rough markers, but sometimes if the segmentation is a harder segmentation, you have to be very exact in selecting the right foreground and background pixels and mark them before you can get a good segmentation. But typically, again, if such an interaction is needed, other simple algorithms like clustering components, for instance, in this case, wouldn't get you anywhere. It's a different approach that has to be taken in order to do a right segmentation. That's on that. Markus, do you see any other questions that you want to?
Oh, some questions are related to what formats we support for import-export. For that purpose, just look up dollar export formats or input formats for that matter, and you will get an idea of the scope of formats that we currently support. Here, QuickTime, AVI for animations, and well, just have a look. Video frames. I cannot really comment on every single one of them. It just would take too long. But this is a good place to start. And then if you have any of these, simply double-click on it and then do F1 or Command-Shift-F, and you can then kind of a reference on that particular format, what's being supported. Some import-export examples here about DICOM, which is a biomedical image format, and so forth. So that may be the most general answer regarding I&O.
One question about erosion. Yeah, one question about erosion and 3D images. Yes, it is supported, as well as a whole lot of more image processing function. I could say probably close to 90% of our image processing functions do support both 2D and 3D. Just check the documentation. In most cases, we should be explicit in what is supported and what is not. Just to show an example, maybe I can even open up this GrowCut segmentation page and point you where to look for it. And in this case, you see that we say GrowCut components work with arbitrary 2D and 3D images. In cases that we don't, it's either the case that the operation doesn't really make sense for 3D, for instance, image effects, adding motion blur, or maybe that does make sense, but doing a posterization effect on a 3D image maybe doesn't quite make sense, so we haven't got there yet. Or due to lack of time, we haven't implemented the 3D version of an operation. But as I said, I'm positive, I don't have the exact count, but we should be close to 90% of operations that do support 3D images. Not much should be missing from the pool. Documentation should exactly say what is and what is not supported.
Maybe Shadi, if I could have the screen again.
Yep.
We should also just mention a few things that we did not have time to cover. I assume some of you do serious image processing, which will be pretty demanding on your hardware. And then Mathematica is maybe not the software well known to be a number cruncher, simply because it is, in most cases, an interpreter. But nevertheless, with library link, it is possible to also take images and move them into dynamically linked C libraries, and this is just a very short little example of how this would work in Mathematica. So if you have a core routine that you really have to make sure runs fast, this would be a viable option, at least one of them. So you would have to load here the CC compiler. Then I have here some C code, which basically loads some headers. You establish the connection basically, and then you can specify here even templates if you like of routines like max value routines, or in this case iColor negate, little routine that basically takes just the pointers to an image and then runs a reinterpretation cast on it, depending if it's a byte, a bit 16, a real or real 64 image, and then does the color conversion right here. And all of that is here used in a color negate command with input output of different image types and so forth. And once this is done, all you would have to do in Mathematica is run create library. I'm not sure if I have all the necessary code. Yeah, I can run this. Specify that the language you're using is C++. The code is the stuff up there. And then you say do a library function load. Assign that to a symbol, and then that symbol now is your function that does exactly that. So if I load here an image, and let me delete this quickly, and I now use color negate, this command will take this image, send it to the dynamic link library out there without any copying overhead, because that link library has access to the data internally in Mathematica, does the inversion, and does that now for any kind of image, color images, color volumes, and so forth. And once you're done, you can unload whatever you had and forget about it. And the same holds true, by the way, but that may be a different tutorial than about GPU programming. Also, that is very nicely incorporated into Mathematica. Back to you, Shadi.
Sorry, nothing else that I want to say right now. I don't see other questions at this point. I think we have gone well beyond the expected time. It's great to still have about 300 people in here among the participants. This shows a whole lot of interest in what we talked about, and this gives us enough motivation to go back and do more material creation and more of these virtual events. If you have any feedback, please send it back to us so that we can include it in the upcoming events. Markus, if you don't have anything else, I would like us to close here and basically, yeah, if anything else from the participant, please feel free to email us and we'll try to get back to you.
Well, oh, thanks a lot, and bye-bye from my perspective here.
Yes.
It's about
Thanks a
that
lot.
time.
Bye now.
Thank you.